This next portion of the video reviews the product and quotient property of roots. In the intro to 5.6 video, we already reviewed these properties, but we were using perfect squares. So 1, 4, 9, 16, 25, 36, so on and so forth were the numbers that we were interested in. Now we're going to look at cube roots. So we want to look at perfect cubes. We have fourth roots, so we'd want to look at perfect fourth powers. I'm going to start off simple and look at perfect cubes. It may be helpful for you to write this down as well. So perfect cubes are going to be like, what is 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. The highest I might go is 6 cubed. I don't expect you to memorize them all, just to show you. If you're ever unsure, you're like, oh, I don't know what 9 cubed is. Just plug in 9 cubed in your calculator. I hit 9, the power button, and 3. So 9 cubed is going to be 729. Well, when I say something's cubed, keep in mind it's just like when I say something is squared. Something squared is that number times itself. Something cubed is going to be that number times itself times itself. We're doing it 3 times. So 1 cubed is 1 times 1 times 1, which is 1. 2 cubed is 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. 3 cubed is 3 times 3 times 3. So 3 times 3 is 9, times 3 is 27. 4 cubed, 4 times 4 is 16, times 4 is 64. 5 cubed, 5 times 5 times 5. So 5 times 5 is 25, times 5 is 125. 6 cubed, 6 times 6 times 6. 6 times 6 is 36, times 6, 216. And you can keep listing them. So when I'm looking at cube roots, I want to look at the factors that are greater than 1 that are perfect cubes. We'll start with 16. The cube root of 16, its factors are, well, 1 and 16, but that wouldn't really help us to pull out that perfect cube. 8 is a perfect cube, and 16 can be rewritten as 8 times 2. And it's not divisible by any of these larger numbers. So I want to rewrite 16 as the cube root of 8 times 2. And I'm doing that because I'm going to end up using the product property, which says if it's two things being multiplied together, we can break it apart. So now what I have is the cube root of 8 times the cube root of 2. So I need to make sure that I write the index, that's the 3, on each of the radicals, or the roots. The cube root of 8 is 2. So this gives me 2 times the cube root of 2. Can I simplify any further? The answer is no, because the factors of 2 are just 1 and 2, and neither of those numbers are perfect cubes bigger than 1. So that's my answer. Next we have the quotient property, which says that if there is a fraction underneath a radical, we can break them apart. It also works in the opposite direction, where if it's broken apart, we can put it back together. It's the same thing with the product property. If they're broken apart, we can put it back together. So here, I'm going to go ahead and break apart the quotient. I need to make sure I write the cube root of 125 over, still showing this is the cube root of 64. And we'll see if we can simplify these. Now here's our list of perfect cubes. 125 is the perfect cube of 5. So I can rewrite that as 5. 64 is the perfect cube of 4, meaning the answer is 5/4. I know it seems a bit tricky right now. Let's keep practicing just to see how we do. Okay. So, when we're simplifying radical expressions, once again, we need to look at the index and try to find the perfect cubes. So I'm going to start rewriting my terms in here as perfect cubes. 27, if we look at our list, 27 is the perfect cube of 3. So I can rewrite 27 as 3 cubed. X to the 6th power, we can rewrite as perfect cubes. So x to the 6th power is x times itself 6 times. So I have x times x times x times x times x times x. If I want to rewrite x to the 6th power as perfect cubes, that would be sets of 3. So I can rewrite x to the 6th power as x cubed times x cubed. Notice how if I think about my properties of exponents, 3 plus 3 is 6. And there were no x's left over. So now I can pull out the perfect cubes outside of the radical, and whatever is not a perfect cube would stay inside. This is a very similar idea to square roots. So 3 is a perfect cube, so I'm going to pull out a 3. X is a perfect cube, or excuse me, x cubed is a perfect cube of x, so I can pull out an x. And x cubed is a perfect cube of x. There's nothing left over, so I don't have to put the cube root of anything. I do have to clean this up though. 3 times x is 3x squared. Part B. I'm going to use quotient property to break it apart. So I'm going to have the cube root of x cubed over the cube root of 7. The cube root of x cubed. That's already a perfect cube. I can go ahead and pull out that x. In the denominator, we have the cube root of 7. Now, the factors of 7 are 1 and 7. So I cannot simplify this at all because 1 and 7 are not perfect cubes that are greater than 1. So I'm just stuck with it. However, keep in mind that we are not allowed to have a radical in the denominator. So we're going to have to rationalize by multiplying by the cube root of something over the cube root of something. Here's where the problem begins. If I do cube root of 7 times the cube root of 7, I'm just going to do that on a separate sticky note so you see. If I do the cube root of 7 times the cube root of 7, like what we would normally do, that would give me the cube root of 7 times 7, which is 49. Or that's the cube root of 7 squared. You can think of it either way. But that's not a perfect cube. I'm still going to have a radical in the denominator. So we want to, instead of having 7 squared, we want to have 7 cubed. Which means instead of multiplying by 7 to the 1st power, we're going to have to multiply by 7 squared. Because if I multiply 7 by 7 squared, I'm going to get 7 cubed. And this would become just 7 because they're inverses. They cancel each other out. So I'm going to multiply by 7 squared. This gives me x cube root of, I'm going to rewrite 7 squared as 49 in my numerator, over the cube root of 7 times 7 squared is 7 cubed. Again, I'm just showing you, hey, once we clean this up, I'm just going to have a 7 in the denominator. Okay, part C. I'm going to go ahead and break apart my quotient using the quotient property. And I'm going to start cleaning it up a little bit. So I'm going to start with the numerator. I would like to rewrite the 16 and the x to the 5th power as perfect 4th powers. So if I'm thinking about 4th powers, I'm not looking at the perfect squares, which are 1, 4, 9, 16, 25, blah, blah, blah. I'm not looking at the perfect cubes that we wrote on the front page, which is 1, 8, 27, 64, 125, so on and so forth. I want to think about perfect 4th powers. So what's 1 to the 4th power? That would be 1. What's 2 to the 4th power? So that's 2 times 2 times 2 times 2. And if you don't like doing that in your head, you can use, 2, hit that little power button, into the 4th power. Look, we get 16. So 16 can be rewritten as 2 to the 4th power. X to the 5th, remember that just means we have 5 x's. I normally do this in class, but it's kind of hard here. Okay, I have 5 x's. I'm going to pull out 4 of them. So 1, 2, 3, 4. These 4 make my x to the 4th power, and I have 1 left over. So I'm going to rewrite x to the 5th power as x to the 4th power times x. See how 4 plus 1 will give me 5? So I'm just rewriting them. And then I have the 4th root of 5. The factors of 5 are just 1 and 5. That's not going to be a perfect 4th power other than 1. So I just have to leave it for now. Let's clean up the numerator first, because we are in a position to do that. I have perfect 4th powers that I can pull out. And when we pull them out, the 4th power and the 4th root cancel each other out. So now, in the numerator, I have 2 and an x pulled out. But the x to the 1st power has to stay behind. So the 4th root of x. Don't forget to include that index of 4. All over my 4th root 5. Now remember, we can't have this in the denominator. We have to rationalize by the 4th root of something. Well, if I want this to become 5 to the 4th power, so I can have a whole number, and I already have a 5 to the 1st power, that means this should be a 5 cubed. So now 5 to the 1st times 5 to the cubed is 5 to the 4th, or the 4th root of 5 to the 4th power. The numerator, we still have that 2x on the outside, but now we have a 4th root times a 4th root. We can use product property to condense that. And then we have x times 5 cubed. 5 cubed is 125, so I'm just going to clean that up a little bit, and then x. If you wanted to leave it at 5 cubed, that's fine. I'm cleaning it up, like I said. Now, last thing I got to do is just make this a whole number. The 4th power and the 4th root cancel each other out, right? They're inverses. So my final answer is 2x 4th root of 125x all over 5.